Let's recap the linear and quadratic Taylor polynomials from Calc 2 and Calc 1. In Calc 1, we used the linearization a lot. And what we always had to do is start with some value of a. We were usually trying to approximate some function value near a, and we would write down the equation of the tangent line. And it would always start out f of a plus f prime of a times x minus a. And we try to get people in Calc 1 to write it that way because in Calc 2 you saw Taylor polynomials. Now, you usually start out with a quadratic approximation. You can also call that T2 or P2. And it starts out exactly the same way. It just starts out at f of a plus f prime of a times x minus a. But the advantage with this one is that it curved, and so you had to add one more term. And so you added one more term. It was going to be 1/2, and then f double prime at a times x minus a quantities squared. Just like that. Now, how did they come up with both the linear approximation and the quadratic approximation? What they did was they just wanted to find polynomials. In the linear case, the only polynomial that went through the same y value and had the same derivative value as the original function at a. For the quadratic approximation, they did exactly the same thing, except they went one step further. They wanted to come up with a parabola, in this case, that went through the same point, that had the same first derivative, and that had the same second derivative at a as the original function. The situation in multivariable calculus is absolutely no different. What we already have this semester is we have a formula for the tangent plane. And remember, we have to have a starting point, f of b plus fx at that same point times x minus a plus fy at that same point times y minus b. And this is a linear function. It goes through the same point as the original function. For example, if I plug in x equals a and x equals b, this turns into 0, this turns into 0, and you get the same function value as the original. Moreover, if you start taking the partial derivatives with respect to x and plug in ab, and take the partial derivatives with respect to y and then plug in ab, you get the same partial derivatives as the original function. We've already seen this. What we would like to do is take this one step further. This is usually about how far they go in industry when they're creating things. What we want is a quadratic function. It will bend like most functions usually bend, and what we want to do is just follow the same procedure as we basically did in Calc 2, at least follow the same pattern. What we should have to have is 1/2 times the second derivative times something squared. And that certainly follows for the first one. So for example, if I have plus 1/2 and then one of the second derivatives, at the point. Now, this is with respect to x, this is with respect to x. What we're going to get here is x minus a quantity squared. Now if we start taking partial derivatives with respect to x and then y, we should have another thing like that. We'll have 1/2 and then f of xy. Remember, that's fxy. At the point, we took the partial with respect to x and with respect to y, so we're going to get an x minus a times y minus b plus 1/2 fyx at ab times again x minus a times y minus b. And finally, there's one more second derivative. That's going to be another 1/2, and this time it's going to be fyy at ab times y minus b quantities squared, like that. That is going to be the formula for the quadratic Taylor polynomial around the point AB. Now, one thing our book does is they say, look, these are usually equal, right? So don't write everything out like that. If they're usually equal anyways, just combine them, right? So what our book will do is just combine them, and if they're equal, you'll just get fxy at ab times x minus a times y minus b. And it wouldn't matter if it's fxy or fyx. I personally like having all this stuff out like this. There are some nice cool functions where fxy is not equal to fyx. If you're a math major, you should absolutely go through that. If you're a STEM major, you should probably go through that. They describe behavior near a point using ordinary looking functions where these don't equal each other, which is really kind of weird. Anyways, and kind of cool. Anyways, that's the formula for the quadratic Taylor polynomial in two variables.